to Ernie, test the test, that would be, if you would, a two-bar stat, wouldn't it? Ernie's first score to Bert's first score. Ernie's second score to Bert's second. That would be a two-bar kind of argument. We're not doing that. We're only looking at Ernie in isolation and then Bert in isolation. So go ahead and grab that one. And then press enter. And you get all kinds of good stuff. Let's wander through it, shall we? Let's wander through it. At the very top, what do you see? Well, it says one of our stats, which is yay. Thank you, TI, for telling me what you just did. Next thing down, what do you see? You see the average of the test scores, 81, which saves us the time of having to crunch things and divide, add a bunch of stuff, divide by a bunch of stuff up. Again, I like you crunching things out by hand once. Or a couple times in your homework. I like that. Get the intuitive feel for what an average is. Understand the computational method. Then I trust that you can do arithmetic. Let's let the machines do it for us. Good. Average is an 81. What's that next thing down there? The sum of the test scores. Tell me your name again. Kelsey, thank you. It's the sum of the test scores. You guys had to do that. So remember the image I gave you guys over here of the spittoon? You throw 83, 82, 79. By the time Ernie throws all 5 of those into the spittoon, there are 405 points in the spittoon. Evenly distributed amongst the 5 data points, there are 81 per pile. So 5 little piles of 81 would add up to the same as his test scores do right now. Fair enough? Solid? Good. Very good. Very good. Very good. Okay, next one down from the summation of x. Exactly. Hey, look at that.
400 squared. 405 squared.
Wait a minute. I got nothing. 5 letters. Is it 5 letters? It's 5 letters. Tell me that.
Sarah.
Sarah, damn it. I'm seeing the 5 letters. I'm not seeing that any letters are. So, it's the sum of the squares of the test scores. So in other words, if you took his 79 and squared it, his 80 and squared it, his 81 and squared it, and so forth and so on, they would add up, the squares would add up to that. This is both that and the summation of x up there. Some of you might be asking, okay, first of all, I have no idea why they're giving us this. I have no clue at all why they're giving us this. I can kind of see why they're giving us this because that would make calculating the average easier. Because you'd have this and divide it by this, but then you might stop and think to yourself, what the hell, they're giving us the average, right? The reason I think as to what, you don't have to worry about these two things for the most part until 244 when we actually use one of them. I think the reason they're still there is due to a kind of historical computation method of the standard deviation. Remember this sum of squares, this guy right here? This summation of x minus x bar squared. Let me go to the sideboard here for a second. I'll swing this over. We'll take a little 5-minute pause for some algebra because algebra is pretty interesting. I know you don't like it all that much, but I think I have an explanation as to why that's there. So sum of squares is this. Write this down only if you're interested in the algebra behind it. Otherwise, you can just zone out for a couple minutes. A lot of instructors make their students calculate this kind of stuff by hand. That's a pain to calculate. That's a pain to calculate by hand because it actually forces you to create that chart and then do that minus that, that minus that, that minus that, and square it all. You can also use some clever algebra. So this looks like something from Math 60, maybe Math 65. Remember the old FOIL method? A plus b squared is a squared plus 2ab plus b squared. Remember that bad boy? Well, you can do that here too. It's the sum of, let's see what this would be, x squared minus 2x bars plus x bar squared. That's what it would be. What was a big table right there? Right there. Now, that, I think, explains those next 2 lines. I think. Because this actually, I'm going to use the word simplify here in the mathematical sense. It's not getting simple, so it's getting much more involved. But if you split the sum across all the terms, you get the summation of x squared, which is that guy up there. You get minus 2x bars times the sum of x, there's your sum of x, which is also up there. And then you've got plus the sum of x bar. So all of these pieces are now up there. Here's the part I don't understand. Exactly, some of you are like, oh my god, I didn't need to see that. That's okay. That's why I said you can just zone out. What I don't understand is, yeah, you go through all this, and then the next line under the sum of x squared is s, which is what you would use to calculate it. So I don't really understand the logic in putting those 2 lines in. That's why they're there, I think. But why? Because the next line down is that beautiful 1.58 that somebody so nicely gave to me earlier after we calculated it. So I don't understand. So I guess what I'm getting at here, friends, is feel free to go ahead and ignore these two lines until, at least if you've taken 244 with me, we'll reference it from time to time. But not this sum of x squared. That doesn't make a whole lot of sense, especially in the context of that's what we care about right there. That's Tabitha's average distance from average, as you so eloquently stated earlier. I have to keep picking on you, but it was a wonderful thing to say. It's the average distance from average. Yeah, I should swing back to here. I'm actually looking at what I'm talking about. Underneath that guy, friends, underneath that guy, this is lowercase sigma. You can ignore him for right now. That's called the population standard deviation, which seems a little silly. It's the population standard, not the sample, but the population. So in order to have the population standard deviation, what would you have to know? In order to know the standard. So imagine doing this. Imagine doing this. You're trying to do that calculation we just did on an entire population. What would you have to know?
Data for the entire population.
Data for the entire population, Corey. How likely is that? Almost extremely unlikely.
Yeah.
We'd have to be able to capture our entire population. Now the computation is a little bit different because it's the population versus the sample. So you can ignore this for now. And we'll talk about when it makes sense not to ignore it anymore, because it does make sense. There are certain times you can deal with a population, not statistically, but probabilistically. And it actually makes sense to talk about that. But we'll talk about that in about 3 or 4 weeks, if you don't mind. Not right now. It doesn't make any sense right now. So ignore that bad boy for right now. Ignore him. So right now, you're looking at two things right now. You like your average, you like your sample standard deviation. They're paired together. This plus or minus this. You can go down further, and it gives you some more fun stuff. You can ignore most of this for right now. We'll get into all of it, I promise. But there's your friend, the median. So no more do you have to go put a bunch of data in a row and go chop, 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 because it'll chop, 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 chop for you. Yay, technology. Hence why we invented technology in the first place. This is the whole point of inventing technology, was to help us do computations quickly. Yay, yay us. Cool? So there's the values we need right now. We'll explore all these other ones. I mean, I think you can understand what min and max mean. You're pretty sure what those mean. But these Q's, we'll deal with those next class or Monday of next week. We'll get into all that stuff. Fair so far? So that's Ernie. That's Ernie. Let's do Bert too. Let's do Bert as well, shall we? Yes, let's do Bert as well. So you already had Bert's data in L2. You already had Bert's data in L2. That's a great place for Bert's data to be. Oh, let me take a pause here real quick. Is anybody using a machine other than an 83? Is anybody using
84.
80? Oh, 80. I'm sorry. When I say 83, I mean 84. They're the same machine. 84 is faster. 84 is faster than 83. Anybody have an 86 or an 89? Okay, that's good. It's not as good. It just makes it easier, so we're all talking the same language. Each of those machines do these things a little bit differently. So we're all using 84s and 83s. Everybody's looking like this. Okay. All right, here's Bert. Here's Bert. So now we're going to go to stat, over to calc. We're still going to do one of our stats. We're still going to do one of our stats. The difference is here, we don't just want to press enter again, because it's going to do Ernie again. We have to tell it where the data is. If you just press enter for one of our stats, it assumes you're looking at L1. So you have two choices. You could delete L1 and put Bert's data into L1, which just seems like kind of silly because you already put it in L2. Or just put an L2 right after that by pressing second 2. And it puts an L2 right after it. So second function, which on this is yellow, and I'm not sure if it's that way on the 84s. Is it blue on the 84s? It's blue. It's blue on the 84s, right? So the second function, and you can see, it's a little blurry on mine, but do you see how above your number keys there's L1, L2, L3, L4, L5, and L6? Yeah. So that's how you call your lists. You actually call your lists from there. There you go. Press enter. And some of this, you might look at this at first and go, wait a minute, hang on. I thought we just did Ernie and got the same values. And then you realize Bert and Ernie did have similar values for some of their statistics, didn't they? They had the same average because their spittoons for their respective doors had the same number of points in them. Because 100 plus 61 plus 68 plus 82 plus 94 adds up to 405, just like 79 plus 80 plus 81 plus 82 plus 83 do. So that's why their averages were the same. And this goes back to our question, who was the better student? A bunch of you said neither. They're both 81 average students. Yes, they are. How are they different? The consistency versus inconsistency kicks in. So you can ignore these two lines right here. But you see how Bert's is different than Ernie's now? He's got different actual test scores, so squaring them is going to give you different results. But that's the magical number I want to deal with right there. 16.6. That's the one I wanted to add to the comparative list. There we go. We can look that up, I guess. So, looking back to our comparator now, I'm going to turn this back on in a second. Looking back to the comparator, who's the better student? Hopefully you're realizing it's a loaded question. There's no correct answer for it. So, a good sideways answer would be, I think Ernie's a more consistent student. On average, they're the same. But Ernie is showing more consistency. Now what's cool is you have a quantitative way of talking about that consistency. On average, Ernie is how far away from X bar? Ernie is how far away from X bar on average? 1.6 points. On average, Bert is, he's about 10 times, if you will, more variant when measured that way. He's also 10 times more variant from a range point of view, as we talked about before, 40 versus 4. But now we actually have a quantification, a way to quantify. So when I asked earlier, I said, okay, Ernie's sample standard deviation is 1.6. What's Bert's going to be? And somebody said a lot more. That's a hard thing to quantify, a lot versus a little. Because what if Ernie had a standard deviation of 1.6 and, say, Snuffleupagus had a standard deviation of 0.16? Well, that's 10 times less than 1.6. Would you now call 1.6 a lot when compared to 0.16? How come, Athena? What are you thinking? What are you thinking?
Well, if I'm thinking of ranges of, we already know that
Bernie, I know it's easy to say.
Ernie is a B student, and he's a Snuffleupagus is, I mean, he still puts him in.
I never told you his average. I just told you he had a standard deviation of 0.16. He may have an average of 42, in which case you go Snuffleupagus needs remediation. but based simply on variation, is he a lot less variant or just less variant? Go ahead, continue your thought though.
Well, earlier you said he had, like, you told us his points.
Yeah, you
It
did
was
give us
99.
his-
Snuffleupagus?
Yeah. Earlier you
Oh, I did make up Snuffleupagus, didn't I?
Yeah, he was all the way up.
So now I'm talking about Oscar the Grouch.
Yeah.
0.16.
Somebody else.
Sorry, YouTube, you didn't hear that. Yes, so Oscar the Grouch, 0.16. But so the point is that what is a large S value versus a small S value? It's really a comparative. It's a comparative. Bert is 10 times more variant than this. This could be 10 times more than 0.16. However, Athena's hitting upon something. There is a low value. There's no minimum possible average for someone. There's no minimum possible average value. You can have negative data. You can. Which means averages can be negative. I mean, we're going to look at one of these on, I don't think we have time to do it today. Yeah, probably not. We're going to look at this next class when we actually average weight loss in a diet program. Weight loss in a diet program. Well, if a diet program is working, quote unquote working, you would expect the average to be negative. So you can have an average, and since you can have a negative average, you can go as low as you want negatively. But there is a minimum value of a standard deviation, isn't there? What's the smallest possible standard deviation you can have? Numerically. For any data set? 0. Kelsey. It's 0. When would you have a standard deviation of 0 in a data set? Say that again. Just so when they're all the same number. So imagine, for example, back to Ernie. Just back to Ernie for a second. Instead of these being his data points, let's treat it in Lucas's balance point of view. Let me swing the camera too so you can see what I'm doing. Let's swing this from a balance point of view. Let's go back to Ernie. You don't have to do this in your notes because I want you to keep your notes kind of as a reference. But let's take that 79 and make it an 81 because we donated some points. Let's make that 80 and 81. Let's make this 82 and 81. Make the 83 and 81. Now essentially, this column is going to be nothing but zeros because you're taking 81 minus 81, 81 minus 81, 81, which means this column is going to be zeros. That's why it can't go below 0 because this value squared will at least be 0, if not positive. But it can't be negative because you're squaring the results. So the smallest possible value a standard deviation can have would be 0. That hardly ever happens because you have to have all data be exactly the same. And that hardly ever happens, as you'll see. There are all kinds of cool random fluctuations. We had to deal with that early on with margins of error. That was the whole point of a margin of error. If you draw a sample, there are going to be variations in that sample. The margin of error adjusts for that. Margin of error technically could shrink to 0 if you sample the entire population, but then it really isn't a sample anymore if you got the entire population. So again, I'm getting a little bit mathy here, but the smallest value this bad boy can have is 0 if there is none. So back to Athena's point about 1.6 versus 6. No, your point was great. You were talking about from a scale. There's actually a 0 value on here. There are different types of data out there in the world. I think there are 4 main categories they often use: nominal, ordinal, interval, and ratio. Now real quickly. Nominal is like, I'm trying to think if I was wearing one right now, like a sport jersey with a number on the back. The number doesn't mean anything. It's just a number that's just like, oh yeah, number 12's got a broken leg. You know, that kind of a thing, right? Although like in soccer, number 10 means something special as the captain, blah, blah, blah. So nominal, like there's not much you can do with nominal data. It's just kind of there. Then you've got ordinal data. Ordinal data is when the order actually matters, but the numbers themselves don't have a whole lot of meaning. That's Likert scale. That's your student evals. So yeah, you can strongly disagree, which is a 1, or you can disagree, which is a 2. But a 1 to a 2 doesn't really mean a whole lot. It's just 2 is bigger than 1, but we don't know how much bigger than 1 it is. Interval data is when 2 is bigger than 1, and we can actually say, oh, it's 1 on a number line bigger than 1. The problem is you can't say it's twice as big because there's no 0 to measure off of. So for example, temperature differences. It was 0 degrees this morning. Now it's 2, which means it's how many times warmer? Well, that doesn't make any sense. It's 2 degrees warmer. You're plus 2. Multiplication doesn't make any sense. Addition and subtraction makes sense. And then there's ratio data, where there actually is a 0. So for example, this is, if you will, by default, ratio data, because you have a 0 that you're working off of, if that makes sense. So that it's not so much data, it's a ratio statistic. So that's what you were talking about, Athena, without realizing you were talking about it. Was you were confounded by the 16.6 to 1.6 versus 1.6 to 0.16 because of the multiplicity. Because you're getting a factor of 10 away each time. The next one would be 166, which would be ludicrous from a test scores point of view. I love looking at this measure when you guys turn in assessments to me. What I like to see are high averages and low standard deviations. Why do I like to see that? High averages, low standard deviations. Why do I like that? It means my class is consistently scoring highly. That's what I want, assuming, of course, my assessments are meaningful, which I try to make them be. So assuming my assessments are meaningful, it means that the lion's share of my students are scoring highly, which means they're understanding at least the topics that I'm assessing you on. What scares me the most are low averages and low standard deviations. That scares me the most. So low average, where everybody's clustered together, which means I'm confusing the hell out of everybody pretty consistently. What I often get at the end of an assessment in some of my classes, not usually 243, I'll get a fairly high average with a fairly wide standard deviation. Now this is a consequence of a lot of things. Students getting burnt out at the end of the term, lots of other assessments coming in. I try to spread stuff around the term so this doesn't happen. But I always like looking at standard deviations because if I have a class average of, say, 78, which is a high C, but the standard deviation is 32 points, then I start saying to myself, well, I don't feel so bad about that 78 because plus or minus 32 off of that runs the gamut from 100 down to 40. Does that make sense? Now that might not make sense in and of itself because you might say to yourself, well, there's some 40s in it. There are some 40s in there. So that's where a graphical attack makes a lot more sense to look at. So the takeaway from today, let's wrap up today. A lot of stuff, a lot of cool stuff, but a few big ideas. Why do we need measures of variation, friends? Why weren't centers enough? Why wasn't just looking at centers of data enough?
It's not specific enough.
Tell me why, Tammy. I love that. I love that. Not specific enough.
Because they both have, like, for example, Bert and Ernie both have the same average.
Good.
But they're plus or minus.
Good. So we might need something else to discern data performance. For example, if you want to buy a copy machine for your office, and you draw a sample of 5 copy machines from company A and company B, and they both average 81, would you be more than willing, who would you be more willing to buy a copy from? Copy center Ernie or copy center Bert? If you're looking for a copy machine. I'm guessing copy center Ernie, since they all kind of behave the same. If you're doing copy center Bert, you run the risk of getting a dud. 20% of the time, or 40% of the time, if you're going by your percentages again. Love that, Tammy. What's the most common measure of variation we use? You got it, the sample standard deviation, otherwise known as just little s. Did you guys catch that it was SX on the calculator? They just do that because that's the variable they're calling everything x, x bar, SX, mean x, that kind of stuff. Beautiful, sample standard deviation. Should you memorize that formula? Should you memorize that formula? No. Hell, you could. I'm not going to make you do it, though. Use the TI to calculate it. What do you need to know about that number that comes out of that calculator? Exactly, Cedar. I want to know what it means. I want to know what that 1.6 or 16.6 or whatever we're going to calculate on Wednesday means. What does it mean? 1.6 what? Points from average on average. Basically, when you think about it, you have to use the word average twice in the definition. On average, how far the data points are from the sample average. That's the big takeaway from today. It took us a while to get there, and I'm glad we did, because now we don't have to go there again to get there. That sounded kind of Dr. Seussish, I apologize. But nonetheless, we'll never have to crunch it again like this again. Okie doke? Okay, we'll call it a day. I can't do what I wanted to do next in 7 minutes. For next time, don't do the homework for variation. It's the next homework step, but don't do it. We'll assign it for Monday. You have a quiz, should you choose to do it, which I think you should because it's a good quiz. And I think it's about Old Faithful. It's fun data. And you have a project. Yes, thank you, Ariana. Project, internal probability. If you get stuck, the lights are off again. These magical lights turn themselves on and off at will.
It's so slowly.